Hello again, Advanced Calc students. This is the 6.3 ICE sheet, which I'm going to somewhat abbreviate. You'll see why here in a second. But this is about L'Hopital's rule, which if you've never learned L'Hopital's rule, we kind of skip it here at Taylor. But the idea is that if you have a quotient and you get 0 over 0 when you take a limit, so you're going somewhere and you get 0 over 0 or infinity over infinity or any other kind of an indeterminate thing, you can do the limit as the derivatives instead. So this is not the quotient rule. You do the derivative and top and bottom is separate. It's kind of what you wish the quotient rule was. That'll be the same limit, and then hopefully you get a limit there. Now, that's not always the case. Sometimes the limit doesn't exist, but if it does, it can pop out when you do this derivative process. Okay, so let's go ahead and talk about number 3 first, which is going to be a few examples of just computing this. And for your first assignment, for your problem 4 on this assignment, you're going to be doing the same thing. I'm only going to do, I think, A, F, and H for the first, for 3, just to show you some tricks. Actually, I'm going to do C, F, and H because I do want to show you an important trick. So let's do C first. So this is 3C. And I'm going to do the limit as x goes to 0 of sine x minus x over x cubed. Okay. Well, if you plug in 0, which is always the first thing you should do for limit, plug it in, see what happens. You get 0 over 0. That means you should use L'Hopital's rule. So this would be the same limit. You get cosine x minus 1 over 3x squared. And I skipped A because on A you'd be done. You get a limit here. On C, you plug in 0. You get 0 over 0 again because cosine of 0 is 1. Well, you can apply L'Hopital's rule as many times as you need to. So let's do it again. And you get negative sine x over 6x. Oh, shoot, I think you get 0 over 0 again. And I'm running out of space. But we'll do it one more time over here. And you get negative cosine x over 6. Now you plug in 0 and you get minus 1/6 as the limit. Not what I expected the value to be. So I had to do L'Hopital's rule 3 times there, but you are allowed to apply it repeatedly. We'll talk about that more here in a second on question 5. Okay, so F and H are more about ways to set up L'Hopital's rule because it only works for indeterminate quotients, but there are other indeterminate forms. These are not the only indeterminate expressions. A couple other ones would be infinity to the 0, 0 to the 0, and 1 to the infinity. The last one seems strange, but it really is indeterminate. If you think about taking the logarithm of it, you can see that you have infinity times 0, which I forgot that one. That's also indeterminate. 0 to the 0 is considered 1 for the Taylor series. If you have an x is 0 and the n is 0, but in general, that's an indeterminate form. So those are all the bad things you could have. So let's look at F here. We're taking the limit as we go to 0 from the right of 1 plus 2x to the 1 over x. And that's why we're doing it to the right, so that 1 over x has a limit which goes to infinity. And so you get 1 to the infinity, which we just said was indeterminate. So the trick here is I'm going to take e to the ln of this thing, which those cancel. And so then I'm going to get, up top, I'm going to use the logarithm rule and get 1 over x, and then ln of 1 plus 2x. And now limits can go inside continuous functions. I believe we've talked about that some, and e to the x is continuous. So I'm going to do the limit up here. And this limit, if you plug in 0, you get 0 over 0. So up there in the exponent, I'm going to use L'Hopital's rule. And I'm going to get 1 over 1 plus 2x. That's the derivative of the top. The derivative of the bottom is 1. You plug in 0 now, and that all becomes 1. So the answer is E. Which is interesting because the original expression didn't have E in it at all. But remember, E's definition is a limit that looks like that. So that goes to that as x goes to 0 from the right. Okay, so that is 3F. And now let's go ahead and do 3H. which has a different trick. So we're going to 0. And it's 1 over x minus 1 over sine x. And so now we are going to do just common denominator to make this a proper quotient. So that's going to be sine x minus x over x sine x. And then common denominator. Now you get 0 over 0. So we're going to use L'Hopital. We're going to do the product rule on the bottom, which is too bad. So now when we do the product rule here, we get sine of x plus x cosine x. When you plug in 0 now, you get 0 over 0 again. So we're going to have to do another L'Hopital's rule. So the top becomes negative sine x. And the bottom, we have another product rule. So that's going to be cosine x minus x sine x. And when you plug in 0 now, you're going to get 0 on top. At the bottom, you're going to get 1 plus 1 minus 0. So 0 over 2. And finally, we can get 0 as the result. So the point of that problem was doing h was common denominator is another trick. So however you do it, whether it's logarithms, common denominator, you need to convert the whole thing to a quotient before you can apply L'Hopital's rule. So that's question 3. Okay, so question 5 asks about a situation where it gives you a problem and then it says, what do we do wrong? I enjoy those kind of questions. So let me write out exactly what they write, and we'll talk about what's wrong. So it's x going to 1, 2x squared minus x minus 1, and then 3x squared minus 5x plus 2. And then they say that's the same thing as doing 4x minus 1 over 6x minus 5. And then they do it again, and they have 4 over 6. And they say, hey, that simplifies to 2/3. What's wrong? Well, you plug in 1. If I'm just going to do the limit, plug in 1, and I get 0 over 0. So I do L'Hopital's rule. Plug in 1 here, and I get 3 over 1. So that was not determinate. It was not 0 over 0. So you stop. And in fact, if you do L'Hopital's rule when you shouldn't, you get the wrong answer. So anytime you use L'Hopital's rule, if it's not indeterminate, it actually gives you the incorrect result. So make sure you check every time you do it, plug in the number again and check if you actually get a limit. So this limit is 3, not 2/3. All right, that's question 5. Question 9 is the next one. The back of the book says just use question 7. So if you look at question 7, it just says that if you want an asymptotes, a horizontal asymptotes. So I want this to be some limit. It says, hey, all you're really going to do is, if you do it sequentially, this is if and only if, for any xn and some n tail to infinity, the image of that should go to L, which makes sense, right? That's kind of how continuities worked for us and how limits has worked for us. So basically, if you take the x's out to infinity, the sequence of y values should go to the limit. That makes perfect sense to me. I'm not going to prove that. But if you believe that, then 9 is pretty easy. So what 9 is asking about is not that fact. That's number 7. We're just going to take that for granted. And you can use that on your homework. That's fine. I don't know if you'll need to. 9 says, well, hey, if you have the limit as x goes to infinity of f of x is L, and then the limit as x goes to infinity of g of x is M, and those are both reals. To prove that the limit as x goes to infinity of f plus g of x is L plus M, and then the same thing for their product is Ln. And so if you use that sequence definition and you just take an x and go into infinity, the point is that you can split these up. So if you think about f of xn plus g of xn, that's the same thing as f plus g of xn. And so you know these limits both exist and are L and M. And you have this fact from sequences that if you take two convergent sequences, you can add them or whatnot. And same thing with product. So that's all they're having you do there is use sequence facts. It kind of seems unnecessary to me, but the takeaway from 9 is that you should know that it's really this result here. You should know that for horizontal asymptotes, you can do sums and products like you want. All right, and then the last one was 13, and 13 has a lot of parts to it that I'm not super concerned about. I don't think you need to be concerned about other than the very beginning of 13. We're just going to do 13a. It says give a reasonable definition for a vertical asymptote, and so we're going to give one. And just make sure that you know that. I'm surprised this isn't just in the text, but it says you have D as the domain, and you're going to R, and D is an accumulation point. Sorry, X is an accumulation point. C, we'll get there. C is an accumulation point of D. So we'll call it D prime, like we had S prime before. So give a reasonable definition, what it means for if you go to C and f of X and you get infinity. Okay, so we're going to do this the same way we did infinite limit definitions for sequences. So we're just going to say that this means for all M and R, and we're really thinking about really big M's, there exists we had a capital N for sequences, but now we have a delta, such that f of X is bigger than that. So I can get f of X as big as I want, bigger than any number, whenever X minus C is less than delta in absolute value. So we're changing the output part to being arbitrarily large rather than arbitrarily close to a limit, just like we did for sequences, but we're still using the delta part rather than the N thing that we did for sequences. So, and I think that is actually in the book. So this is 13a. The answer's in the back. That's a definition to have on hand for vertical asymptotes. The rest of the problem is kind of clunky, and I'm not so concerned about that. All right, so that is the ice sheet for 6.3, which is the end of the material for exam 2.